All right, let me pull my chat up here. All right, we are live. Audio and video is up. Welcome to Statics. All right, so let's talk about housekeeping. Attendance grades are up to date. The last homework was submitted it was due today, and so the only, I guess, homeworks left are the bonus homeworks, and we'll talk about that here in a bit. They actually just opened like a minute ago, but before you do them, I wanted to discuss some logistics about them so that you're aware. Now, just to make sure that everybody's on the same page, I assume, did everybody get a chance to mess with the at-home game? Did everybody see that? Okay, good. That I always get that question, and I thought it would be a good thing to add so that you all have an idea of where you're at and whatnot as the semester ends. Okay, let's talk about the bonus assignments because they opened today. Okay, there are 2 bonus homework assignments that I've added that will add to your homework average. Okay, so first off, there's the course eval. If you do the university administered course eval, hold on, let me check. You might refresh your page. Refresh your course content page, and they should be there now. But before you start doing them, just hear me out. So for the course eval, I don't want to see what you wrote. I just want to see that you did them. Okay. If you upload a screen capture telling me that you've completed the course eval, I'll add some bonus points to your homework average. And then there's the course learning outcome survey. So the course eval is the one that's administered by the university. The course learning outcome survey is the one where we discuss the specific outcomes in this class. Like, do you understand trusses, or do you understand centroids and things like that? For the course learning outcome survey, make sure to not do the survey twice. You could actually click the link and do it twice. Just don't do it twice. When you complete the survey, there's a window that pops up that says, hey, you've completed it. If you upload the screen captures that show that you've done that, I'll give you an additional allotment of bonus points. And I've had a couple people email me screenshots of their course evals, but if you could do me a favor and upload to Blackboard as well, that would really help, because then I'll know that you did it. I don't want to lose it in my inbox, and so if you did it, I want to make sure that you get the credit. And do me a favor, and if you want the credit, make sure that you complete the survey and also upload. Like there are instances where, if you do the survey, but if you don't upload the confirmation to Blackboard, like I won't know that you did it because it's anonymous. Like right now in one of my other classes, I know that 11 people had done the survey, but only 9 of them had uploaded the confirmation of Blackboard. So 2 people did the survey, and I don't know who did it. So make sure that I know so that you get the credit you deserve for the survey. Okay. Any questions before we talk about the final? Okay, let's talk about the final. So the first thing I want to get across is the final is not going to be, whoa, somebody drew on the screen. What? Oh yeah, the links are at the bottom. No, you're fine. You're fine. I'll clear it. I wanted to make sure that if there are any questions that we answer, that's no big deal. All right. So the first point I want to get across is that the final is not going to be administered any differently. It's just another test. The only thing is it's longer. Okay. So You've had 3 exams with me in this class. The 4th exam is going to be just the same thing, a bit longer. It opens at 12:45 on Friday, December 11th, and it closes at 2:45 on Friday, December 11th. So it's a 2-hour exam. So for our other exams, you had an hour to do it, and they were designed to be 50 minutes long. Now you've got 2 hours to do it, and it's designed to be 100 minutes long. So it's no different. And I'm going to give you, just as before, I'm going to give you time to upload the PDF. I'm going to have that upload close at 4 p.m. So that way you aren't going to feel rushed for the time limit. It's open book, open notes. You can use anything on Blackboard. You're not permitted to give or receive aid from another individual. Don't do that. You've got more than enough resources to complete the exam. You can access the recordings, the lecture notes, all that stuff. It's going to operate the same way on Blackboard, so it's going to be forced completion. So once you start it, it's got to be completed in one sitting. It's going to be timed with an auto submit feature. So after 120 minutes, it's going to submit. And then the questions will appear all at once, just so you can review your responses before submission. As for the format, again, it's basically just the previous exams, just a bit longer. It'll probably be something like 8 to 10 short answer questions. And again, the short answer questions on these exams are just that, short answer, like no more than 1 to 2 sentences, keep it short. And I'm probably going to have, I'm thinking 5 computational problems. So we've had 3 on previous exams. It's probably going to be 5 on this exam. Again, type out an answer for every question, even the computational ones. It helps out with grading. Don't just answer the questions on your scratch work if you can avoid it. Okay. As for the topics, it's the class. So, I'll say that anything is fair game. The one thing I want to point out, I'm not trying to trick you. I'm really going to try and avoid asking the most esoteric thing I can think of. And I do my best to try and ensure I'm not double dipping on stuff. Like I don't want to have 5 problems where you have to compute the support reactions in every problem. Some of this stuff, as you know, some of the topics bleed over into others. So, but I'm going to do my best to ensure that the 5 problems are fairly independent and are not super tricky. I'm not trying to do that to you. It's just general coverage of the course. So what have we talked about this semester? So first off, the fundamentals. Make sure that you understand classical motion, you understand Newton's 3 laws, that you can compute the weight of an object. Think, back on, day 1 when, this was new stuff. Now, just the weight is so basic. Make sure that, you can convert units and perform dimensional analysis as appropriate, and that you can employ concepts in algebra and trig. I guess I should add calculus to that, but really, we haven't done much calculus in here, and I don't intend for this to be a Math 229 exam or anything. But some of the concepts are important. As for units and dimensional analysis, we really haven't done a lot with that this semester. I just want to make sure that you understand the basic units that we use in here. The first exam, really the star of the show, was particle statics, so that you understood the properties of vectors, that you were able to add vectors, and that you could apply equations of equilibrium for concurrent force systems. So remember, a concurrent force system, or a particle, is when all the forces all intersect at a common point. And so that's what we meant by a particle. And so what made particle statics different from rigid body statics is particle statics, we didn't need moments. We could just look at sum of forces in the x direction, sum of forces in the y direction, and if it was 3D, sum of forces in the z direction. And so as a result, you do need to be able to solve 2x2 and 3x3 systems of equations. And so that's where your Casio comes into play, or whatever calculator you're using. I don't care what calculator you use as long as it's not, another person. Rigid body systems and rigid body equilibrium, this was exam 2. So this is, being able to compute cross products and dot products. So if exam 1 was all about adding and subtracting vectors, exam 2 is all about multiplying vectors. And remember, there's 2 ways of doing that. We can, there's a scalar product where the multiple of 2 vectors is a number, a scalar, And then there's a vector product where the multiple of two vectors is another vector. And so the cross product is the vector product, the dot product is the scalar product. And then the cross product R cross F is the moment. That was the formal definition of a moment is R cross F. I mean, the numerical magnitude is just the magnitude of that force, and then the term D, which is the moment arm, the perpendicular distance from the force to the point in question. And so that's how we compute moment about a point. If we dot that moment with lambda, a unit vector about a given axis, that will tell us the moments about that arbitrary axis. And so if you wanted to find moments in 2D, you could dot that with a k vector or whatnot, and there's your moments in 2D. Make sure that you can resolve force couples, and so remember what a force couple is: two forces of equal magnitude, opposite direction, separated by a distance. That you can convert that into just a single moment, and that you can generate equivalent force systems in 2 dimensions and 3 dimensions. And so that's when you have a rigid body and there's a bunch of stuff on it, a bunch of forces. And so let's take that and resolve it into just a single force and a single moment, or just a single force a certain distance away from a given point. And finally, rigid body equilibrium, that's just support reactions. That's just determining the external forces required to keep the rigid body in equilibrium. Exam 3 was centroids and structural analysis. And so centroids, make sure you can determine the location of the centroid of a line, an area, or a volume. And then that moment of inertia topic, make sure that you can handle that if necessary. And then structural analysis, really the 2 stars of the show there were trusses. Make sure that you can determine the internal forces in a truss, either with the method of joints or the method of sections, whichever makes sense, and that you can draw the shear and moment diagrams. I put on here reactions because you need to be able to compute support reactions in order to determine the, you need to be able to compute support reactions in order to determine those internal forces, but it's not really a separate topic from rigid body equilibrium. The only thing really, really new on this list is friction. And so I will tell you that you're going to have at least either a conceptual question or a computational problem on friction. I know friction is like the newest topic, and it hasn't been on a test before, so it will be on this test. I'm just go ahead and tell you, but it's not the be-all, end-all star of the show. We've, where there's plenty of other stuff to discuss. The last thing I wanted to show you are the references, and what I basically did is I compiled all of the meat and potatoes, if you will, of the course, like everything that I think is the critical slide. So you can sort of think of each of the lectures as music albums, and this is the greatest hits. So first off, we've got the fundamental equations and concepts, so that gravity, the weight of an object is mass times gravity, and then all of the fundamental equations and concepts that we've assessed throughout the semester. The big thing is that you understand the base units. So like masses in kilograms, forces in newtons. And so what is a newton? It's a kilogram times a meter per second squared. Make sure that you have an understanding of that. Trig. Trig, I think, is let me say one thing about trig. You obviously need to be able to manipulate trig, functions and so on, and compute, relationships between rectangular and polar. That stuff is important for the course, and no way is that not an important topic. The one thing I would point out about trig, and I mentioned this during the last exam review, is I think that you should think about when you need to break out the trig functions and when you don't need to break out the trig functions. There were some times during some of the exam problems where you're given a slope ratio and you're like, okay, I need to compute the angle by taking the inverse tangent and then take the sine and cosine of that angle to get the x and y components. But you can just use SOHCAHTOA, just the adjacent over hypotenuse and the opposite over hypotenuse, and it would be a lot faster. So like while it's important, make sure that you're being as efficient as possible, because there's, you want to make it easier on yourself, not harder. Vectors, make sure that you understand how to add vectors, that you understand that vector addition, the idea of the tip to tail rule associated with vector addition. So, P plus Q can be found by just taking P and Q and stacking them tip to tail, and then just, striking that line between them. You can also take a vector, split it up into X and Y components, and then add up those separate X and Y components. And then, how did we express vectors in X and Y components? We use the IJK vector notation. And so remember, IJK are just unit vectors along the X, Y, and Z axis respectively. And so it's just a convenient way of writing vectors in 2 and 3 dimensions. This slide has a lot of really good stuff in it. So this is our vector expressions in 2D and 3D. So we can describe vectors with IJK. We can compute the magnitude with basically just using the Pythagorean theorem. Remember, we notate that as like we use that absolute value term. That's what we mean by the magnitude. To add vectors, we can just add up the X and Y components. That was the value of splitting things up into the IJK expression. And then our equations of static equilibrium, this is for particle. I guess I should put here a note that these are equations of static equilibrium for particle statics. So sum of forces in the X, sum of forces in the Y, sum of forces in the Z direction. Those are equations of equilibrium if the oh my goodness, I am a popular guy. Go away. Those are equations of equilibrium if the forces all meet at a common point. If they don't, then you have to incorporate moments as well. And then the orientation of vectors, if you want, like, remember, this is when we had a bunch of vectors all meeting at a common point, and we wanted to determine the resultant, but we also wanted to determine the orientation of that resultant. And so, in 2D, we're just looking for an angle, and in 3D, we can determine a unit vector, and then the unit vector, the coefficients of I, J, and K are the cosines, the directional cosines of that resultant. Next, we go to exam 2 land. So we've got cross products and dot products. Remember the cross product, there's a couple of ways to do that. You could do the Saris rule, or you could do cofactor expansion. But remember the concept as well. A cross product is, if I have vector A and vector B, what is the cross product A cross B? That vector points normal to the plane containing A and B, and then the magnitude of that vector is the area of that parallelogram formed by those two vectors. The dot product, if the cross product is related to the sine of that angle, the dot product is related to the cosine of that angle, and it generates a magnitude. Or a scalar magnitude, not another vector, but a constant multiple. Then our formal definition of a moment. Formal definition of a moment is R cross F. R is the position vector. It starts at the point about which moments are taken, and it ends at any point along the line of action of F. And then the magnitude of the moment is basically just the magnitude of the force times the moment arm. So yeah, and I think we sort of hit that, into the ground. Moments in 2 dimensions. So, if we're only looking of a moment, let's say for a vector in the XY plane, then, our moment by the definition is going to spin about the Z axis. So a lot of times all we really care about is the magnitude. And so we can compute that very easily. And then moments about an arbitrary axis, we take R cross F and we dot it with the unit vector along that axis. It starts anywhere on the axis about which moments are computed, and it points anywhere along the line of action of F. Force couples, again, we can take those 2 vectors and replace them with just a single moment. That's the magnitude of that one of those forces times the distance between them. And there's the definition of a force couple. Equivalent systems of forces, that's when we split the That's when we split the rigid body that has a bunch of different forces on it. We resolve it into just a single force and a single moment. And I think we did a fair job of covering that then. Here's just some of the reactions in 2 dimensions and the support conditions in 2 dimensions and the support conditions in 3 dimensions. And then we get into exam 3 land. We're in, moments of area. So this is, how we started to develop the expressions for the centroid. The first moment of area, the second moment of area. The second moment of area is called the moment of inertia. So that's what that was. And then don't forget, it's really a good idea on the exam to have your centroid references handy, both your 2D centroid references and your 3D centroid references. I also went ahead and threw the formula for the moment of inertia, the parallel axis theorem. Remember, D is I'd say the one term that's a little unique, and that's the distance from the centroid of each individual shape to the centroid of the whole composite shape. And then we have our references for the moments of inertia as well. Method of joints and method of sections, the 2 approaches for solving a truss. Remember, method of joints is a bit more appropriate for solving the whole truss. Method of sections is a bit more appropriate for solving a particular member in a truss. I know the one on the exam that we had, it was just a small truss, so really didn't matter. Our derived relationship between load, shears, and moments led to the conclusions for our graphical approach, which was really where the money was. And then this was our shear and moment diagram relationship that we developed for concentrated loads, as well as the one for distributed loads. And then really the only super new slide that you haven't seen before, well, I mean, yeah, I guess you have seen it because we did it on Monday. It's just a single slide with everything related to static and kinetic friction. Whew. We have covered a lot in this class. We've done our share of work. Man, I need a second. All right. That is not just, the material on the exam, but that's the class. That's statics. We've covered a fair amount. So we have, 30 minutes. We don't. Yeah, I know what you mean. We've got a fair amount of time, and I don't want to waste the time. We also keep in mind we also have all of lecture on Friday to address any questions and anything you might have. But I want to open it up to see if there's any questions about just anything, about the exam, about anything we've discussed, what have you. And, there was a lot there. I know. I went through 36 slides of just formulas and equations. So I'm sure it's probably like, I got to take that in and process it a bit. And that's why I wanted to, give you the time to process that between now and Friday, so that on Friday we can, start to dig into it a bit. But floor is yours if there's any questions. I want to make sure that you have your your say. So floor is yours. I'm sure I know that. Okay, oh, here we go. We never did anything with moment of inertia, did we? Well, we had a homework assignment on it. It wasn't on the last exam. Let me hold on. I think it was 5.5, was it? Yeah, it was homework 5.5. But it was not on the last exam. Oh, okay, hold on. Let me see. One thing that kind of slipped. That's understandable. Okay, so one thing that kind of slipped on me is when we were doing methods. Okay, that's a good question. And then Josie, I think you're right. There was a problem on one of the exams about if you had a beam, like how do you determine the strongest orientation? And it's whichever has the largest moment of inertia. Mr. Adams brought up something about method of sections, and I think I can answer that one pretty easily. Give me 1 sec though. I want to pull up the class notebook here. Give me a second. Okay, here we go. Give me 1 second. Let me share the screen on this. Okay, so let me back up a little bit. So this was a problem that we did in class. This was a truss analysis example that was specifically focused on looking at the method of sections. And so walking through the problem a bit, we'll take our time with it, but we had to first determine the support reactions. And the goal of the problem was to determine the forces in the 3 members along that section with the green line. So members EG, members FG, and members FH. So the first thing we did was we computed the support reactions, and we got that BX was 16 kips to the left. We got that JY was 33 kips up, and BY was 23 kips up. All right, so hopefully, is everybody good on the support reactions? Like, I hope I don't, like, for the purposes of this problem. Like, I mean, if we want to do a discussion of support reactions later, I'm more than happy to, but is everybody okay if I kind of just move past that? Okay. So we cut a section, and I chose to look to the left. And with this problem, I don't know that it really mattered whether or not I looked to the left or looked to the right. I do tend to believe philosophically that you should cut a section and look towards the direction that has the least stuff going on. You know, make the problem easier for you as the engineer to analyze. So but for this, whether or not you cut a section and look to the left or look to the right, you still got 3 forces to deal with, so it really didn't matter. So I cut a section and looked to the left. And so when you cut a section and look to the left, this is what you've got. So there were 3 moments. Let me erase some stuff because there's some highlights here that don't really matter all that much. Okay, erase this, erase that, erase this. Okay, so that way we're kind of looking at something from a frame of reference here. Okay, so here's the problem, and maybe I'll do this. Maybe I'll label one other thing. So we'll call this F, F, G, Y, F, F, G, X. Okay, so here would be what you would see as the student or as the analyst before you begin summing forces and summing moments. Okay, so I cut a section, I look to the left, and I have the 16 kip reaction, the 23 kip reaction, and then the 28 kip load, the 3 loads in red over to the left. Those are what we found by, you know, equilibrium of the structure and what was already on the structure. The unknowns are the internal forces in the 3 members, the EG, the FG, and the FH. So from a strategy perspective, when I look at this, so we took the diagonal and we split it up into X and Y components. So how many unknown horizontal components are there? There's 1, 2, 3, right? But in terms of vertical components, there's only 1, right? So the first thing that I did when solving this problem is I said, let's just sum, let's just sum forces, come on, get rid of that. Let's just sum forces in the Y direction. So by summing forces in the y direction, I got FGY, and then the slope ratio gave me FGX. So before I move on, are you okay with that? That the first thing that I did was sum forces in the y direction to give me that vertical component of that diagonal. Okay. So then the question becomes, okay, you know, I can use sum of forces in the y direction to give me that one. And if I have that one, then I have that one. So this member's figured out. So then becomes the summing moments. Whenever you sum moments, what you want to do is sum moments wherever two of the forces intersect, okay? Because you want to make it easier on yourself. So I propose that really you should sum moments either there or there. Okay, so let's take G. If I sum moments at G, then this diagonal member and this all intersect at G. And so by those forces intersecting at G, it isolates that FE8 or that FH at the bottom. And so by summing moments at G, I would be solving for FH. Likewise, I could sum moments at F, and that would eliminate that diagonal and that horizontal member at the bottom, and that would isolate EG, and I could solve for EG. So the short answer to your question is, always sum moments at a location where the unknowns intersect. Did that answer your question? Good, good. And I think on this problem, what we did is we summed moments at F. No problem, no problem. Yeah, we summed moments at F to isolate the EG. That's what we did up here. So we've got plenty of time. I know we got 17 minutes in this lecture, and we've got our whole lecture on Friday. But I mean, this is good stuff. I really want to make sure that we're going through all this. I'm sorry. I'm a bridge engineer. My stuff sits still. Because unless they're drawbridges, they don't move. Well, no. I have never worked on a drawbridge before. No, I mean, but you have to move things to make a bridge. That's Dr. Bryce's problem. He's the transportation engineer. I appreciate the compliments. I mean, I'll say this is my first time ever teaching statics, and in all seriousness, the comments that you all put on the course evals and the CLO surveys, like I really hope I get to teach this class more often, and I always want to make sure that we're doing better. I certainly the coronavirus and the pandemic tested my the limits of my understanding of what was possible. But when we move back, I mean, there's definitely room to improve the class, and so any of your feedback, I really will take to heart. But I appreciate the compliments, though. You're right. But it's not we don't really consider it a dynamic effect. So when you take Engineering 216, you will learn about thermal expansion. No, thank you. So to answer your Well, good. I'm glad. I'm glad you all enjoyed it. I had fun teaching it. I do have my limits, but I can't help going back to the question about thermal expansion. So the way that thermal expansion works is, at least with what you're talking about, is well, I could wing it, yeah, I guess, is there are three parameters that affect how much a bridge will expand and contract. There is the length of the bridge. There is the change in temperature, whatever that change in temperature is, and then there's what's called the coefficient of thermal expansion. And the coefficient of thermal expansion is just a property that's inherent to a given material. So every material has its unique coefficient. One of the things that's unique about steel and concrete is that steel and concrete have very similar coefficients of thermal expansion. So if you heat up a bridge that contains both concrete and steel, the steel doesn't expand at a different rate than the concrete does. So it doesn't crack that way. It's actually a really serendipitous parameter of both materials. But the way that you handle that from a design perspective is twofold. One, the bearings that you use usually will have, so you'll learn this if you ever go into bridge engineering land, is you'll have one bearing, which is what the bridge sits on. It's called a fixed bearing, and the other side's called an expansion bearing. And the expansion bearing actually, it's allowed to move a little bit, but it's not like dynamics where you're chucking a particle down the road. It's a very slow expansion. Now, thermal expansion can generate a lot of force, but it doesn't move fast, so you don't really consider it to be like a dynamic effect. The other way that we handle it is through the actual bearing devices themselves. The most common method that we use is what's called an elastomeric bearing. It's basically a vulcanized rubber pad with steel plates inside that allow a little bit of wiggle at the end because of end rotations and the expansion. So, all right, I went off on a tangent there, I know, but you started asking about bridges, and I had to answer. Why is it? Hold on, let me see. Why is it in examples that you have a roller on one side and a fixed point, but in real life the truss isn't going to move? That's actually not true. So, so let me show you a couple of things. So, I'm going to show you a beam example, but just because it's less to draw, but the idea is kind of the same. So do you all know what I mean by plan view? Like, plan view is if I'm in the helicopter looking down, and that's what I see. So let's just take a look at a beam, right? So this is a beam in plan view, okay? So I'm in the helicopter looking down, so this, would be a beam that's supporting a bridge. So there's like a base plate element right here that the beam sits on, and like a base plate element here that the beam sits on. And so one of the things I mean by fixed bearing and expansion bearing is on one side, you might use like holes to bolt that down, but on the other side, you might have slotted holes. So it actually is allowed to sort of move a little bit. So that actually is, like, we actually do allow that to happen. Yeah, and so that's actually a really good question. Now, here's another thing that's worth pointing out. Now you got me going off on tangents here. So let me show you something. This is a steel design aspect for you. So if we're talking about like beams in a building, the facts are the beams really aren't going to be seeing much load left or right. They're really only going to be loaded up and down. Like the beams that are supporting the weight of this office are really only seeing vertical loads. In building design, the only time you ever experience lateral load is with two things, either wind or earthquakes. So, but for most gravity loads, just goes up and down. And so one of the things that we to handle this is the way that we connect steel beams. So do you remember me using the term simply supported? Do you remember me using that? So okay, so simply supported, I might not have actually used the term here, but a simply supported beam is just one that has like I'm going to talk about that here in a second, but short answer is kind of yeah. So this is what's called a simply supported beam. So it just has a roller support on one end and a pin support on another. It's a very common analysis model that we use in civil engineering. And the way that we would build this in real life is, so let's say you have an I-beam, okay? So here's the beam, and then here's the flanges, right? So what I'm doing is like here's the beam, right? So hold on. Like if you looked at the beam on the sides, like here's the I-beam, but if you looked at it on the side, you would see like the flanges and then just the main body of the web. So that's kind of what I'm looking at here. Simply supported beams, when you connect them to the column over here, so like let's say here's a column. So if you wanted to connect this and you wanted it to be like simply supported, what you would do is you would only connect like the webs, right? So like here's the beam, and so if you connect it just with the web, we would treat that as simply supported. But if you wanted it to be a fixed connection, like you wanted it to be a cantilever, you know, something like that, then not only would you connect the flanges, but you would connect, or sorry, not only would you connect the web, but you would connect the flanges as well. The idea is that the flanges are really what carry the moment, but the web is what carries the shear and the reaction. So we only do this in very, very specific locations in the building. Basically the places where we're trying to make sure that the building can withstand wind and seismic. Otherwise, we just use simple connections. So, sorry, I went off on a tangent there. Now you say, is that why a lot of bridges have the bumpy segments? Are you talking about like the finger tooth connections? Yes, actually, you're exactly right, Mr. Adams. You'd have those mostly on the outside. We pick certain sections of the building that are designed to withstand wind and seismic, and we design those for those additional forces. And everywhere else, we usually just keep it simple. So those are called expansion joints, and that's exactly what you're talking about here. That's what they're designed to do, is expand and contract. They tend to be a real problem from a maintenance standpoint because, yeah, structurally they behave exactly the way that you want them to, but then they get a bunch of gunk inside them, and then that gunk, you know, when you get gunk inside them, they don't expand and contract the way that you want. I mean, you get leaves and rocks and all that stuff, and so they have to be cleaned out pretty regularly. So it's a challenge from a maintenance standpoint. The common, or the current state of the art is to try and use what are called integral abutments, where you cast all of that together in one big slab to try and eliminate that joint. And a lot of new bridges use integral abutments. So newer construction, we try and avoid using those joints whenever possible. You got to be real careful how you detail, you know, your abutments and your bearings and stuff like that. But yeah, we try and avoid it. It is a maintenance challenge. Man, I'm going off on bridge topics, man. I could talk about this stuff all day. I want to make sure I'm answering static questions too. Yeah, but you could, well, I mean, yeah, but keep in mind, you know, think of a bridge on I-64 that's got, you know, 4,000 vehicles a day, and we design bridges in the United States for 75 years. So that thin material over 75 years of traffic, you know what I mean? The thin layer issue. Well, come on over. We're happy to have you. Now you gotta find your passion and go for it. Well, now hold on. I don't know that I would call, you know, the civils the Sith or anything, you know. Okay. There's yeah. Well, you still got a little bit of time. We still have like 4 minutes now. I know we have a whole nother exam review on Friday, but are there any other quick questions for today? Well, here, I tell you what, we went through a lot of slides today, and I mean, there's been a lot of work we've done this semester, and I know that it's a lot to keep in your head, you know, the first time you learn it. So why don't we do this? You all, you know, take these notes, review them. You don't have any homework assignments between now and Friday, other than the surveys. Like, if you could do that, again, really appreciate the feedback. But chew on it for a bit, and then on Friday we'll come back, and I won't have like really any announcements. I'll just say, okay, let's get started, questions, and we'll spend the whole time just reviewing any questions. If you don't have any questions, we'll end class early, but I want to make sure that I'm there for that full 50 minutes in case you need me. So all right, I guess I'm going to go ahead and call it. We'll end a couple minutes early, but again, you chew on it, and on Friday we'll continue our review. That's all I have, everybody, and I will see you all on Friday. We're going to stop the recording and go ahead and log off. We'll see you then.